Example number 4. For the function graph in figure 7-2i, letter A, identify the kind of function it could be. Letter B, on what interval or intervals is the function increasing or decreasing? And is the graph concave upward or downward? Letter C, describe something in the real world that a function with the shape of graph could model. Letter D, find the particular equation for the function given that points 210 and 56 are on the graph. And letter E, confirm that your equation gives the graph in figure 7-2i. So we have exactly the same requirements to get as example number 3. So this is our graph on the bottom left, figure 7-2i. So for number 1, or letter A or number 1, okay, identify the kind of function it could be. Now you could notice that this graph tends to go to the positive x-axis. This is the y-axis, but it does not contain the origin. At the same time, it tends to approach the x-axis. So it tends to approach the x-axis, but it seems not to touch it. So in this case, we are going to hypothesize that it could be a quadratic function because it could open, or what I mean is it could go like that and then form a vertex here and then do like that. So it could be a vertex at this point or anywhere somewhere here before it rises. Okay, so this could be a quadratic function. At the same time, it could also be an exponential function because it does not touch the x-axis. So our assumption here would be that we are going to take the exponential function. Why exponential function? Because of the fact that it does not touch the x-axis. Number 2, on what interval or intervals is the function increasing or decreasing? And is the graph concave upward or downward? Notice that the graph goes downward. It opens upwards, meaning that it's concave up. So it's concave upwards, right? Okay. So its curvature tells us that it's concave up. But it also goes downwards. It's concave up. And at the same time it goes downwards. So it is decreasing. So aside from a concavity which opens up, it is also decreasing for the given domain, for the given x values. Notice your y decreases entirely over the entire domain shown. But we are not sure if this graph is extended to its maximum domain, which is not shown, then it could be a quadratic function. But as we have assumed, it could be, it's most likely an exponential function. So over the graph shown, we are taking the hypothesis that it is concave up and it is decreasing. Okay? And letter C describes something in the real world that a function with the shape of graph could model. Anything, any real life scenario. Like, again, we would take the exponential decay, the decay of a certain radioactive materials such as cesium-137. Cesium-137, which was, in a way, in a case, an explosion of cesium-137 happened in Chernobyl, Russia, which is part of the Soviet Union before, and the cesium-137 exploded there. Okay? And the radiation of the cesium-137 in 1986 left around 1,000 kilograms into the atmosphere of Chernobyl. So of course, as time goes by, that 1,000 kilogram radiation that was left or was in the atmosphere of Chernobyl in 1986 would tend to have an exponential decay over time. So possibly that by 2066, for example, let's assume there is 157 kilogram left. So as you can see, the decrease is exponential. For a course of over 80 years, okay, the containment into the atmosphere of the cesium-137 became 157 kilograms, which is still not safe for the habitation. So by 2066, still not safe. So around wait for maybe another 40 years or 20 years before it becomes habitable, because the radiation is not safe for human habitation. Now that's a real life example of this exponential decay. It is decreasing and concave up, posing an exponential decay example. So that's our example, the explosion of or exponential decay, okay, in general. Radioactive decay, okay, the proper term is specifically, okay, radioactive decay also. Okay, letter D, or number 4. Find the particular equation for the function given that points 2, 10 and 5, 6 are on the graph. So we are to do this on the next slide. So we have the same figure, and because we assume that it is an exponential function, therefore we would set up the general form of our exponential function, which is, what is the general form for the exponential function? We have y is equal to abx. For power function is ax raised to b. Now for exponential functions we have abx, and our a and b are element of real numbers, and b cannot be equal to 1, because if b is equal to 1, then we will only have a times 1 raised to x, or just a. So b cannot be equal to 1. Therefore, we could define two equations again, because we have two unknowns and we have 2 points. What are the 2 points given? We have point A. Let's call it point A, the upper point. So it's 210. And our B is equal to 5, 6. Substituting the values of x and y for both points A and B, we will get, for the first equation, we will get 10 is equal to AB raised to 2, or AB squared. For the second point, we will have 6 is equal to AB 5. That gives us two equations with two knowns. Therefore, we could solve the variables a and b. And how are we going to do that? How are we to do that? Okay, this is the method. We would get the ratio again of the two equations. So let's start with, I would like to get 2 divided by 1, or 2 is to 1. So I would have, what do I have here? It's 6 over 10 would be equal to AB 5 over AB squared. And we could just cancel our A So we will have now 6 over 10, or in other words, it would be 3 over 5. We divide this, we simplified it by dividing both numerator and denominator by 2, and we will have b cubed here on the other sides. Am I correct? And 3 over 5 is just 0.6, 60%. So let's make it a ratio. And we will have to get rid of our 3 here. So we divide both sides by, or we raise both sides, rather by 1/3. And now we could cancel our 3 here. So our b now is equal to 0.60 raised to 1/3. That's our b. How do we get our a? Okay, to get our a, we have to substitute oops, it's not the right arrow. Okay, we have to substitute, so let's put it here. Why do I want to do this, okay? Why is it like that? Okay. So to get our a, we will select any equation from the two. So let's choose number 1. So for number 1, we have 10 is equal to a, and our b is 0.60 raised to 1/3, and then it is raised to square. This will give us 10 is equal to a 0.60 raised to 2/3, right? So our a then is equal to 10 divided by 0.60 raised to 2/3. And if we are to get the exact value of our exponential function, then we will have y is equal to, our a is 10 over 0.60 raised to 2/3, and our b is equal to 0.60 1/3 x. That is the exact amount of the values of a and b. Now, if that's exact, but we could actually make use of decimals. So a is, taking into account the calculator, a is 10 divided by 0.60 raised to 2/3. But we don't have any function here that would give us that kind of value. So we will use our scientific calculator. If you have a scientific calculator, you can also do that. So our a is 10 divided by 0.60 raised to 2/3. And our a will be 14.0572. Just do it like that. So y equals a 14.0572, 0572, and then our b is 0.8434 raised to x. This is raised to x. Okay, so this is our equation. This is our function. Okay. Let's put it here for better sight. So our equation is y is equal to 14.0572 times 0.8434 raised to x. Now letter E says that we have to confirm that our equation gives the graph, which is represented by this, the one that you see on there on our left. So how do we prove that? We plot the graph through the use of our graphics calculator or our grapher. Okay? And also note that our B is in between. Your B is 0.8434. Am I correct? This is our B. So notice that this B is in between 0 and 1. And if our B is in between 0 and 1, the postulate says that our function is decreasing, which is indeed decreasing. You could see that our curvature is decreasing over the given or the shown domain. Okay? So therefore, we are certain that our function, that the one that we got, is the correct equation for the graph that appears here. So that solves our example number 4, an exponential function.